Hello everyone, this is Deborah Calderola, a PhD student from Polytechnic di Torino. I'm here to introduce you our work, Cluster-driven Graph Federated Learning over multiple domains. Before diving into the details of our work, I would like to start with introducing you the reasons why we think federated learning is an important framework and why it will have a great impact in the future. So, why was federated learning introduced? The main reason is pretty simple. There's a huge quantity of data of great value for the world of machine learning, which is privacy protected and therefore unusable. I'm thinking of medical data or the data produced by the sensors of the Internet of Things, or simply the pictures taken with our smartphones. In 2016, McMahon and Al introduced their solution to issues related to data privacy and data access, which is the new framework by the name of federated learning. In a standard architecture, there's a global model which is kept on the server side. During each round of communication, the server sends the global model to the online clients, which train it using their local data. After training, the clients send back the updated parameters of the model to the server. That implies that the server never sees the actual data, therefore preserving privacy. All the client's updates are collected on the server side and aggregated according to a chosen algorithm. Consequently, the global model is updated. The main algorithm used for the updates aggregation is called federated averaging, which is based on a weighted average of the parameters, where the weight is given by the number of samples seen by the client at training time. Now I ask you to imagine the following scenario. We want to learn a global model able to classify images of animals, and most of our users come from Europe, so that means that the pictures will most likely be of dogs, cats, and birds. But what if at some point some users from Canada join our distribution, so with pictures of moose and beavers, or from Africa with lions, or Australia with kangaroos and koalas, and so on? At this point, will our model be able to address the different data distribution? The answer is obviously no. This is where our contribution comes into the picture. We propose a new algorithm by the name of FedCG to address the statistical heterogeneity in federated learning. We found ourselves in the standard client-server architecture where clients have different data distribution. There's one global shared model, and the algorithm used for aggregation is federated averaging. In the first step, FedCG clusters the client's local data according to their distribution. In particular, we refer to each different distribution as a domain, and we make the realistic assumption that clients may have data belonging to different domains. The federated clustering is based on two domain classifiers, which are sent from the server to the online clients. Their training is based on a teacher-student paradigm, and in particular, each domain classifier maps the input images to a probability vector, which is defined over the possible domains. At training time, the teacher provides the domain's pseudo-labels as target for the student's predictions, while the student's parameters are learned through a process of knowledge distillation, by minimizing the cross-entropy loss between the students and the teacher's predictions. The student's parameters are then updated at each round of communications with the standard FedAVG, while the teacher's parameters are updated with the student's ones every 3 rounds, in order not to bias it towards the last seen clients. The second step differs between training and test time. In particular, at training time, given the domain pseudo-label extracted through clustering, domain-specific parameters are selected and added as residuals. If we take a closer look at the model, we can see how the lower layers are domain agnostic, while the upper ones contain a residual domain-specific information. Moreover, in order to share knowledge across domain and in particular across similar domains, we make use of a graph convolutional neural network. Each node of the graph convolutional neural network contains domain-specific parameters, and the weighted edges allow us to model the interactions among domains. Specifically, given the domain's pseudo-label extracted by the domain classifier, the node containing the corresponding parameters is selected. Thanks to the connection of the graph, domain-specific parameters are produced and are added as residual to the last layers of the network. Their addition is weighted by a learnable parameter. Then the global learned model is sent back to the server for the standard aggregation. At this time, we make the realistic assumption new clients might appear, and they might bring them unseen data distributions. Therefore, exploiting the subpredictions of the domain classifier together with the connections of the graph, we address the new data distribution as subcombinations of the known domains. For example, in this case, the second client has access to pictures of skyscrapers, which represent the red domain, while the third client has seen seascapes in yellow. At test time, a new client appears with pictures of skyscrapers over the sea, which is an unseen domain. Therefore, this new domain will be the weighted combination of the red and the yellow domain. We experiment our model on the Celebay and feminist datasets from the LEAF benchmark. In particular, we compare FedCG with the federated averaging baseline and with other important federated learning algorithms. In both cases, FedCG outperforms the baseline, and specifically in feminist, where the dataset is more heterogeneous and therefore the impact of the graph is more important, the results are even better. We invite you to check out our paper for more information. You can find here my contacts for more details, and I thank you all for listening and wish you a good day.